Okay, so we start the class. Today we want to do implementation of support vector machine and support vector regression. Oh, before that, I explain what is support vector regression. That sounds pretty different from support vector machine, but still the methods have some similarities. Yeah, and after that, if we have time, the exercises we do. One exercise basically from the textbook. Yeah, and I uploaded the chapter 9 lab slides maybe 30 minutes ago, so you can check the slides. Slides have a lot of outputs, but in reality, it doesn't have much content. So, okay. And your final project, you can add more analysis if you would like. So we haven't covered tree-based methods or splines or support vector machine when you wrote a final project plan. So you can modify it as you want. And I think that to get a good grade, important thing is to compare at least two methods. For example, one is linear model and the other is the random forest. Then you can compare with cross-validation, or in some case, the validation approach. Then you will get the full credits as long as your analysis goes well. So comparing two methods are not easy. So that's a kind of goal for this class. So if you do only linear regression, probably you won't get the full credits, but to compare two methods in a good way, that certainly deserves full credits. Okay, so chapter 9. Okay, so sorry, I have to share the slides. Yeah, so support vector machines. Support vector machines is, sorry, I think I, yeah, so support vector machines is a classification technique, and which basically maps all observations, entire data set, into the higher dimensional space. Then we separate the two groups linearly. I mean, separate two groups by a hyper plane. So in case of, for example, suppose we only have the one variable x to explain y, and we map the just one-dimensional predictor space into two-dimensional predictor space by using x and x squared. Then we have the two axes. So if we have two axes, then we have a plane. So we separate two groups by a straight line. So that is the idea of the support vector machine. If we use the high-dimensional space, it's called feature space, then usually the separation works better. But it's really hard to intuitively see what's happening. So if we use, for example, x to x to x and x squared, maybe x squared isn't really a very efficient way to describe the data. So maybe x and square root of x is better, but the support vector machine is pretty automatic method, and we are not really sure what's happening in the feature space. And support vector machine, actually the feature map phi is not explicitly described, and we only have the kernel, which is made by this feature map. So it's even harder to see what's happening. Okay, so now, okay, so that was anyway, so the classification problem. So suppose that we have the feature space and that we have two classes, and that we separate the two classes by hyperplane. So certainly this is classification technique, and the idea is to classify with the maximal margin, so the distance, minimum distance between data points and the observations is maximized. So how to use this idea for regression? That is actually a non-trivial question, right? So when we define logistic regression, that has a lot of additional ideas to linear regression, right? So now we go a kind of backward. We only have classification rule, but we have to develop a regression technique based on this idea. So it's a kind of new idea, and it's not covered in the textbook, but certainly, we wanna have a regression model in addition to classification model. So that's why I think it's useful to discuss it. And suppose that the x in RP, so p-dimensional vector, predictor vector, and y is just the continuous, the response variable. And suppose we have n observations, x1, y1 to xn, yn, and we have some feature map. So defined in the same way as support vector machine. Then we consider y is equal to beta naught plus beta transpose times phi of x plus e. Then this can be a regression model, right? So phi of x is, for example, this map. So in this case, this corresponds to just the polynomial regression. So we can basically use this feature map for regression model. But the support vector machine have several additional ideas, such as to maximize the margin, and also we allow some exceptions by cost function C. So those ideas should be used to get something, to make this something different from just polynomial regression or basis functions. So support vector regression minimize this quantity. Okay, so linear regression or polynomial regression or basis functions, that we just minimize for all observations yi minus beta naught minus the beta transposed phi of x. Phi of x is a kind of function of vector x square, right? So the least square method minimize the sum of residual squares. But here the difference is we have v here, and we have the lambda times the norm of beta here. So what this means? So at first the v, if the v is just a quadratic function, v of x is x squared, then that's just the same as this. But generally that we can have different v. And for support vector case, that we use this v. So this v is, okay, if we use a graph, it's written in this way. So this is the v of z. So y is equal to v of z. So this is usual least square method. So the residual is penalized by square of the residuals. But here the support vector regression, that we don't penalize if error is less than epsilon in absolute value. But after that we penalize the linearly. So there are several differences. At first, this is called epsilon insensitive loss function. So if error is small, then we don't change it. Okay, so that simplify the situation, right? So if data fluctuate, you know, along the trend line, the small fluctuation does not matter for this support vector regression. So that makes curve slightly smoother. And the next one, yeah, so epsilon, so the shape of the function. So this green one is quadratic, but the red one is linear. So basically more robust against outliers. So those are the two differences. So this is a kind of strange because if we have large epsilon, the most data are ignored, right? If the data have only small residuals, basically those are ignored. So basically that we have very special observations. We focus on very special observations, and we basically fit the model so that the all special observations are, you know, explained well by the model. So it's a kind of special idea here. So V is different from just a square function. And the second term is the size of beta. So it's similar to rich regression. So we penalize the size of parameter. So if we have too complicated vector phi of x, then we can explain the training set well, but the test set may not. So we penalize the large size of beta. So the too complicated model we penalize. So then we can get the regression result. And here lambda and epsilon are hyperparameters. So lambda is similar to the lambda in rich regression or lasso. And epsilon, this is a new one. And it's hard to say, but for different epsilon, our model is different. If epsilon is large, only, you know, observations with the very special characteristics are accounted for. Epsilon is very small. Basically all observations matter for the result. Yeah, so this is the idea of support vector regression. So yeah, so we have epsilon sensitive function. So if we have observation around here, it doesn't really matter. So yeah, maybe it matters some, but the point is that for example, this observation moves to here. That does not matter because it's within the tube with the width of epsilon, the radius of epsilon. So it doesn't really matter. So the only observations which matters are observations out of this range. So it's a kind of, you know, outliers and so on. So basically these observations determines the curve. So these yellow observations determines the curve. Yeah, I think it sounds strange. I think still, I explained this many times, but still it sounds strange for me. Sometimes we ignore outliers, but the only outliers matter. That is a little strange. So yeah. So maybe authors don't believe that this is very useful. So maybe that's why they skipped. But yeah, at least sometimes it's better than other regression methods. So at least it automatically accounts for nonlinear effects of X on Y. So this is the theory for support vector machines. Some textbooks have different explanation, but essentially the support vector regression has this loss function. So I think that, so it's also explained by using the cost function without using this lambda and V. but yeah, but anyway. So this is support vector machines. There are maybe some other expressions, but they're all equivalent to this. Okay, so now we wanna do lab session. Do you have any questions for support vector machine and support vector regression?
Professor?
Sure.
I think it was the last lecture, and is also pertaining to the quizzes that were due yesterday.
Mm-hmm.
I think we're measuring C, and then
Oh yeah, yeah.
Then you mentioned at the end that the numbers are all of M.
Mm-hmm.
I'm not really sure what you had meant by that.
So probably this kind of question, right? So it asks the size of C, right? And the size of C is a little complicated because it's relative to M. So basically the total error size is M times epsilon. I think M times epsilon. Epsilon over M is C. Epsilon over M is epsilon over M is C. Yeah. Maybe okay. So we got the example here. So yeah. So maybe I explain the example here. So we have the margin M. Margin M is calculated within the procedure of support vector regression. Suppose M is 2. Then okay, so these three observations, observation number 1 and observation number 8, and only 2 observations. Yeah, anyway, so only 2 observations violates the rule. And in this case, okay, so suppose that from the graph, the epsilon 1 is slightly smaller than M. So epsilon 1 maybe 1.4, and epsilon 8 is about maybe 0.7, right? So in this case, relative to M, epsilon 8 is 2 over 0.7. So epsilon 8 over M is equal to 0.35, and epsilon 1 over M is equal to 0.7. So C is equal to 0.35 plus 0.7. So it's equal to 1.05. So this is how to calculate C. So C is relative to M. So C is the size, the total exceptions allowed. And the observation 1 and 8 are exceptions. And observation 1, they uses the 0.7 of that exception. And the epsilon 8 it has the 0.35 of the exception. So in total, the C is 1.05. So in that quiz, you have to calculate M. Actually, M is asked in B, question B, but you have to calculate M first. Then evaluate the the error size. Then you have to get this C in this way. Yeah. So in this case, both epsilon 1 and epsilon 8, if divided by M, it's less than 1, but sometimes it's more than 1. If more than 1, we have the observation the other side. If observation 1 is here, maybe M is, this number, 0.7 becomes maybe 1.3 or something. If observation is here, actually the error size for this observation relative to M is maybe 2.1 or something like that. Yep.
All right, that makes sense. Thank you.
Yeah, sure. Any other questions?
I had a question regarding that same question too, actually, because I was able to get in the quiz the second and the third one right, but not the first one in which we had to calculate C. And as I was looking online, I was wondering do we ever use a negative M to calculate C?
No,
so like,
M is always positive.
Okay, thank you.
Yeah, in that question, I think yeah. Yes, in that question, I think the total distance from here to here is given as m. So you have to divide this by 2, but m is always positive. Any other questions? Okay. Yeah, all quiz questions are 100% original, I think. So if you search on the internet, then maybe you can understand how to solve it, but you can never find the answer itself online. Okay, and we do exercises. Yeah, so chapter 9. So it may be too complicated. So I don't use the R console, but just use this, the R markdown file to explain support vector regression. So I explain both support vector machine and support vector regression. So at first, it's just the support vector machine with linear kernel. So linear kernel means just we use the original data space. So just the linear separating hyperplane. So it's essentially similar to LDA or logistic regression, but the cost function is different. So results are slightly different. So we have the margin M, and also we have allowed error size. So everything is different in terms of loss function, so slightly different. Okay, so first the SVM function is in the library E1071. So this is a strange name, but this package has many important functions. And this is data generating process. You don't really have to follow in detail, but basically we define 2 classes by random numbers, but in such a case, there's no difference in characteristics. So one group, we add 1 to X coordinates. Right? So basically the blue ones and red ones are just the normal random numbers, but the red one is shifted by 1. So originally red one is the 1, the left of each observation. So the blue and red don't have any difference in characteristics, but now it's shifted by 1. Red circles are shifted by 1. So maybe the separating hyperplane, I don't know, maybe like this or something like that. Yeah, and how to fit this? So here the y is the response. So it's -0, 1 here. You can see the y is -0, 1, so binary variable, and x is the 2-dimensional, the continuous variables. Then we can fit y on x by this. So yeah, at first the SVM parenthesis y tilde dot means the all other variables, and the data is D, so that's it. And the kernel, the radial kernel is default, so we have to change it into linear kernel. And the cost function, that is the total size of errors, the exceptions allowed. And the scale, if is true, then x and y are scaled to the mean 0 and standard deviation 1. So in our case, we have 2 predictors. So we standardize it, then results may be slightly different. Here, I don't really scale it. Probably the result does not change much because originally the x1 and x2 are both generated by the same procedures. Maybe some parallel shift will be made, but the other than that, it's similar. And this is the result. Okay, so just that we fit the SVM, and the object is SVM fit. Then we plot SVM fit, and this is the data set. So basically, we calculate the fitted class. And support vector machine is not probabilistic method, so we cannot get fitted probability. So we can just get the the classification results. And this is the classified as, so this part is classified as -1, and this part is classified as +1. And the crosses are support vectors. Here. We cannot really see, but these crosses are support vectors. And the color of each dot represents the the actual class. The color is actual class. Sorry. So that means this area, the wine red area, the classified as +1. So red class, I would say. And these points have the color of the red color. So that means the classified correctly. But this one, you can see that this one, this is the classification error. So only one classification error in this case. And yeah, it uses some numerical procedure. So this has some zigzag pattern, but that should be linear, actually. And then this shows which are support vectors. Okay, so you can see that, for example, these observations don't matter to determine the straight line, but only these crosses that matters for to determine the boundary. So to determine this boundary, these the blue ones, the blue circles and blue crosses. Sorry, the blue circles don't matter, and only these crosses matters. You can see that we have 8 support vectors. I think that you can see we have 8 crosses, maybe 2 here, 3, 4, 5, 6, maybe 7. Sorry. So we have 7 support vectors. Yeah, but this figure is probably not really essential for support vector machines. I mean, if more than 3 predictors, we cannot describe in this way. Right? So this is only for 2-dimensional space. Maybe 3D graph can describe up to 3 predictors. Yeah, and we have several. This is the summary of this result. The support vector machine has several different parameterization. So usually we allow the C. This is the total size of exceptions, but sometimes some transform type of parameter such as new is used. So there are several types. So this is the type, and kernel linear, as we have already seen, and cost function, the cost value, the 10. If we change it, then result may be different. Yeah, I think the cost is small, probably. Yeah, I don't know. Yeah, cost is small, then probably it's simpler rule. Yeah, so if we change the cost, then the boundary may be different here. is the result. So sorry, the cost is small, maybe more complicated, maybe. Cost is small. Oh, I'm not exactly sure if this is exactly C or some function of C. Because if cost gets smaller, 0.1 compared to 10, actually we have more support vectors, so we have more exceptions. So it's not clear, but the size of M is also different. So yeah, it's not very clear. But anyway, so if we change the cost, then we have different regression results and we have different support vectors. And yeah, I think that if we have more support vectors, then the boundary is a little more complicated in general. And here the cost is different, so we have different number of support vectors. Here we have more support vectors. And yeah, then now we want to optimize this cost function. And basically you can change the cost little by little, then we can try what is the best cost value. And the result that isn't really sensitive to the small change of cost. So usually the cost is in exponential scale. We just use the 0.001, 0.01, 0.1, 1, and we have 5 here, but then 10 and 500, 100. Then this code, the tune function, that optimize the hyperparameter in SVM. And this is the summarized result. So actually we can see that this cost has the lowest error rate. So cost is 0.1. So sorry, what is cost is 0. Cost is 0.1 here, and we have one exception. And cost is 10. Sorry, yeah, cost is 10 here. It sounds we have the same number of misclassified observations. No, actually, yeah, not sure. It sounds only one misclassified, even cost is 10. One, two, three, four, 5, 7. And here, 10. Yeah, but this is cross validation. Sorry, this is just in sample error. Okay, so we fit the 20 observations, then just use the fitted results. So basically, we use the data to explain data. So it's not a fair prediction. But if we do cross validation, if the cost is 0.1, the error rate is only 5%. But if cost is larger, the error rate is 15%. And the cost is smaller, the error is 55%. So this is optimal. 0.1 is the optimal, the cost, the hyperparameter. So we should choose the cost equal to 0.1 for this case. Yeah. Yeah, also we can use the best.tune function to automatically see the results for the best support vector regression. So number of support vectors is 16. Yeah, so now the so now that we want to have a method to calculate the test error. So if we repeat this, then we can calculate cross-validated error. So yeah, so now that we generate larger number of observations with the same rule. So just randomly generate the predictor values and add 1 to x1 value for the class 1. And class -1, we just leave it as is. So basically, label with 1 is shifted by 1 to the right. So that's why we hopefully separate two groups. And we use the best SVM model, and we use the test data set, and then we can see that this is the prediction performance. And actually the prediction performance, then we have the 22 misclassified observations here. Yeah. And this is with cost 0.1. And cost 0.01, that we have the 27 misclassified observations, so 22 and 27. So certainly the 22 is smaller than 27, so the cost of 0.1 is better. Yeah, but actually this is much worse than the previous results. Previously, the CB cross-validated error is only 5%, but here the 22%. And why this is much larger? Just the data have some randomness, and original data set only have 20 observations. So that's the main reason. If the training set have 1,000 observations, probably the training error and the test errors are similar for this. Oh, sorry, this cross-validated error and the test error are similar, probably. Yeah, hyperparameter is one arbitrary number. So if one arbitrary number is optimized, then probably it underestimates the cross-validated error slightly. So probably the test error is slightly larger than cross-validated error, but larger training set, probably the difference isn't that large. And what's this? The separable case. Yeah. So this is the separable case. So this is basically based on the same procedure, but just luckily that we can separate two groups perfectly by probably this straight line. So in this case, maybe we don't want to allow exceptions. Yeah. And I think that this cost parameter is probably the inverse proportional to C. So we want to make the C's equal to 0, right? So I think that the cost function is yeah, so I think that this is a little different from C, and the larger cost corresponds to smaller C, I believe. And in this case, linearly separable, so we don't allow any exceptions. So we want to make the cost larger, so we want to make C smaller. So we make the large cost, then we can perfectly separate two classes with the 3 support vectors. You can see that basically this observation, and this observation determines M. Probably the slope is slightly larger negative value. I think these 3 distances should be the same. So I don't know where is the best line, but yeah. Yeah, and just the other things are similar. The similar graph of support vectors and the classified regions. and different cost makes different separation rule. I think this is perfect separation, and this is not perfect. Yeah, so these are the support vector, I mean, the largest margin classifier. So now that we want to do nonlinear pattern. So linear pattern is anyway covered by logistic regression and LDA. So nonlinear pattern is more important. And this is just the data generating process. So you don't really have to care about it. So we generate random numbers from 3 by 3 square. So x1 value is from negative 1.5 to positive 1.5, and x2 value is negative 1.5 to positive 1.5. And within this, I make the circle with radius 1. So we have two true classes. So one is this yellow area, and the other is outside of this area. And this yellow area is 1 times pi. So this area is pi. And outside of this area, 3 by 3 minus pi. So this is 9 minus pi, approximately 6. This is approximately 3. So we have two classes. Within the circle, about 1/3 probability, with about 1/3 of probability, it happens. And outside of the circle, it happens with the 2/3 of probability. So this is the graph. Okay, so maybe the x scale and y scale are not the same. So this is basically a circle. And here it's ellipse, but yeah. And we do the support vector machine in 3 ways. So one is linear kernel. So linear separation. Linear separation does not make sense. So possibly we separate at this line, left-hand side, the more red circles, and right-hand side, more black circles. But it doesn't make much sense. And the second one is the most, probably the best one, polynomial kernel with the quadratic terms. So basically, we can use x1, x2, x1 square, x2 square, x1, x2, and intercept. So this boundary is described by x1 square and x2 square. So this should be sufficient. So this is very good for this classification. So probably it will perform best. And the third one, the polynomial with d is equal to 3. So that means we have x1 cube or x1 square, x2. So some variables are redundant. So probably it hurts the result. So remember that, for example, even linear regression, that we put redundant variables, then actually the test performance gets worse. So maybe it includes most necessary information, but also it includes redundant information. So probably it's worse. And the last one is radial kernel. So this maps entire space into infinite dimensional space in a good way. So it's a kind of the it can fit all. It can fit all. So it should be somewhat good, but the P2 is really, a kind of spot on support vector machine for this specific example. So probably the P2 is better, but it should perform reasonably well. And the first one, so linear regression, linear kernel. We have 83 support vectors, basically more support vectors, more complicated pattern. And the polynomial kernel, we get the support vector, only 4 support vectors. So pretty simple, the classification rule. And the polynomial kernel with degree 3, 85 support vectors. So it struggles to identify what's the true rule. So rule is very complicated. It's determined by 85 factors, 85 observations. And last one, 34. Probably it simplifies the rule somewhat. Thanks to the the infinite dimensional space. And then the results are here. So this is the linear kernel. And at first, you can see that all areas are yellow. So that means all observations are, all predicted values are -1. So remember that the red one, so within circle, the area is only pi, and with the outside of the circle, the 9 minus pi. So 9 minus pi is larger. So their conclusion, the support vector machine's conclusion is that all areas are, false. So that is outside of the circle. So within the circle is small. So that is just, error. So that is the result that linear support vector machine made. And the second one is the polynomial kernel with degree 2. It almost correctly identifies the relationship. So the one group is within this circle, and the other group is outside of this circle. And most observations are correctly specified. And some errors, maybe, I think the errors are maybe here, one error, and the other error here, and maybe here. I don't know, but they're mostly correct. And this is probably the ellipse with some angle. So because of the data randomness, it doesn't correctly specify the circle, the unit circle, but probably it's ellipse with some tilted the ellipse probably. And this is the third degree, and actually this doesn't really work. So again, all observations are classified as false, so outside of the circle. So it doesn't really work well. And unfortunately, so basically the cubic terms just ruin the result. And the last one, radial basis kernel. This is based on infinite dimensional space. So this boundary is complicated shape. Boundary has complicated shape, but actually they're mostly classified correctly. We have some errors here, maybe some errors here, and some errors, maybe at least 2 errors, but it works good. So probably this is the best one. And this is the second best one, and others does not make sense. And now that we calculate training error and the test error. And first, the linear kernel. And remember that all observations are classified as false. So truth, okay, so we use this table format, the predicted value and the truth value, and we can calculate the predicted class as predict function with this support vector object. And this is the data set. Then we can say almost the, so it does not make much sense. So all observations are classified as false, but actually the 61 the false observations and 39 true observations. So 39 observations within a unit circle. So it doesn't make sense. And the test data, okay, so still about 1/3 the true and 2/3 false, but it does not make any sense. And the polynomial kernel with degree 2, the training set, it classifies everything correctly. So actually, I don't know. So original figure, it seems some exceptions here. So I don't know what happened here. I don't know why this is inconsistent. Yeah, I'm not exactly sure about it. At least we see 2 exceptions. Sorry, I'm not exactly sure about the exceptions, but the training set, we have 2 observations, two exceptions. So sorry, training error is 0. So we have no exceptions and everything is classified correctly. And the test set, Sorry, maybe this is the test set. SVM D3. D3 is what? D3. Yeah, sorry. So we have originally the data set D3. And we use first 100 observations to use the test, to use the first 100 observations as training set. Sorry. So this graph, this scatter plot is based on all observations of D3. So it includes both test set and training set. So I think that it's probably not appropriate, but it includes both training set and the test set. So that's why we have the test errors here. So training set, actually it's perfect. And the test set, we have 2 exceptions. So 98% correct rate. So error rate 2%. And polynomial kernel with degree 3. So training error 39%. It doesn't make sense. All observations are classified the false. And the test set, just the all observations are classified as false. It doesn't make much sense. And the radial kernel, actually the training set, it classifies all observations correctly, but the test set, we have the 3 errors, error rate of 3%. Yeah. So probably most of the cases, the radial kernel works best. Maybe we have to optimize some parameters. So that is the classification by support vector machine. Yeah, we didn't really optimize the parameters, but in next section I did a little bit. Do you have any questions? Okay, so 9.6.x support vector regression. So this is not covered in the textbook, but we use the famous Boston housing price data to apply this method. So library must has this Boston dataset. Boston dataset have 14 variables and 506 observations. And the house price is MEDV, median house value of each town. So observations, one observation is one city, one town. And 13 other variables to explain the house price. For example, the zoning, I'm sure that what's the exact meaning of ZN. And this is crime rate. And this is the maybe proportion of industrial area. And this is environmental variable, the concentration of NOx, number of rooms. This is the average, the spec of the houses, average age of the houses, and the distance from city center, and so on. And I make training set and a test set. And based on training set, we want to fit support vector machine, and we evaluate with the test set. And we just randomly determines the indices for training set and the tests. And I fit the linear regression as a baseline. So this is the baseline model, and we use the stepwise procedure to drop some variables. And this is the final model, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So probably we dropped one variable, and then we keep all other variables. And so this is the best model, LMB, then fitted value, and we calculate training MSE, root mean square error, and test MSE. Training 4.65, test the 9.38. So it overfits the situation. So training set, the error size looks like 4.65, but actually, if we do test error, that is 9.38. So how about support vector machine? We can do the same thing, the median house value, and we use all default value. So the epsilon size is 0.1, cost value 1. And the gamma is, I think, the automatically the determined. So yeah, so the yeah. So gamma is the parameter in the inner product. I think the inner product of vector x and x prime is defined by the exponential of the distance between x and x prime, and that we take square, then the I think the divided by gamma. I mean, maybe multiply by gamma anyway. So negative gamma or something. So this parameter is automatically optimized and 0.076. So still, these two parameters can be optimized, but we use the default value. And what happens? And the training error is 3.35 compared to 4.65. So it is significantly smaller probably. And the test error is the 8.93. That isn't fantastic, but slightly smaller than linear model. So it's support vector machine, even without any parameter optimization, it performs at least slightly better than linear regression. And I optimized some parameters, radial basis function and cost function 0.1, so it's smaller. So probably it allows more exceptions. And epsilon is 0.5, so basically we ignore more observations, I think, yeah. So epsilon insensitive error function. So epsilon is large, basically we ignore the smaller residuals. Then training error gets much larger, but actually the test error gets smaller. So before, the training error is 3.35, so it gets much worse, but actually the most important, the test error gets smaller. So just the original model overfit the situation, and real performance is 8.93, but here 7.68, so it's much smaller. So if we optimize parameters, then we get better results. We can use the tune function, the tune function, to optimize parameters. Actually, I just manually change parameters and find a good value. Any questions? And machine learning methods, the less plots and the less interpretation. So just based on the performance, we have to decide based on the performance. But at least it's good to see some graphs. So I calculated fitted values. The SVR, dollar signs fitted, the returns the fitted value for each observation. So this is for training set. So I describe the median the median value of the house and the fitted value. And we can see that we have the positive relationship. It's a positive correlation. So model makes some sense. But also that we can see that we have some trouble around here. Maybe we have to separate the expensive communities from others to make a prediction. So that is one implication. Except for this area, the fit is pretty good, but this one pretty different. And maybe one reason is the median value is censored at 50. More than 50, it's censored. So maybe that's the reason we have some problem here. And this is test set. Maybe we have less trouble with these observations, but the relationship is a little vaguer than before. So correlation gets smaller. So always training set, it works better than test set. So it's natural, but the test set still, the predicted value makes some sense. And here linear kernel with some different cost function. So linear kernel means they're almost the same as logistic regression or LDA. And no variable selection, so possibly it's worse than the linear regression. I optimized some cost functions, cost parameter and epsilon parameters, and the epsilon is very small, so probably almost ignored. Just usual, the V-shaped curve. Epsilon is very small, so almost a V-shaped. Maybe some flat area here. And the cost is small, so we allow more exceptions. Then actually, training error 7.14, actually it's probably the worst since the beginning, but the test error 8.12. This is better than linear regression. So in this specific example, the support vector machine with some hyperparameters perform better than linear regression. So that means quadratic loss rather than quadratic loss, the epsilon sensitive, this, the piecewise linear function that works better for this data. Yeah, so in this way, then we can do support vector regression. Yeah, but remember that the support vector machine and the support vector regression are not very popular these days because people think that the performance isn't as good as neural network. Do you have any questions? Yeah, I think that we don't have really enough time to do exercises, so I will upload the exercise questions, but maybe we stop here. So do you have any questions? Maybe final projects or quizzes? Yeah, so next time I will discuss a little about neural network, but only one class. So maybe I just make an introduction to neural network.
I guess I do have a question about the final project.
Sure.
You said comparing models. Do you mean comparing different, I guess, algorithms, or do you mean like, oh, this model has this predictors and this one has this predictors, which one's better?
I thought that just to compare two models in terms of prediction performance. So for regression analysis, maybe the root mean square error, cross-validated root mean square error, and the classification maybe, I don't know, maybe average AUC or maybe average error rate by cross-validation. Yeah, but also but also it's good to see what predictors are used. Yeah, that's true. Yeah.
So not necessarily two different algorithms, right?
What do you mean? Because different models have different algorithms. So, you mean different algorithms of the same model?
Yeah.
No, I don't intend that. Just the different models. Yeah.
Okay. All right. Just making sure. Okay.
Sure. Any other questions? Okay, so if not, I stop here. So see you on Thursday. And from next week, we will start final projects.
Thank you. Have a good night.
Okay, see you.